Thank you, and thanks for being here. Thanks for inviting me to talk about my research and about the things I've learned over the past few years of doing this. Because when I started my PhD, I knew very little, if not to say nothing, about neutrons and neutron science, especially for archaeology, because it's still not a very common technique for that. Um, I will be talking about um, why neutrons are what we're using. Sorry, it's just that my notes disappeared, but I will live with that. Why I'm using neutrons, perhaps how to choose the best source for your needs, what questions to ask, and so just how to prepare before getting to the stage of using neutrons for your artifacts before and also what can happen and kind of what to expect a little bit. And here are my supervisors, Anna, Federico, and Antonella Scarillo, on Ines beam with diffractor detectors at the back. To begin with, how has my research started? It was a PhD, and we're looking at Iranian swords from the Iron Age, which were unfortunately trafficked into the UK in recent years. And they were intercepted by the Border Force, which means that then they contacted the British Museum because they have a long established track record with such cases. And so they liaise with foreign institutions and foreign governments to inform them, that these artifacts have entered the country so that they can be repatriated. So that's what's going to happen. They will be sent back to Iran eventually. But for now, we were given permission to analyze them scientifically. And while we don't know exactly where they come from, looking at stylistics, looking at the appearance of the swords, I was able to link them to certain provinces in Iran, where they might come from. And they definitely come from different sites, slightly different provinces, but it's impossible to tell exactly from which site. If you're not sure why neutrons are a good probe for your artifacts, they are non-invasive and non-destructive, which is the greatest appeal for them. That's why we generally talk about neutrons for cultural heritage and not archaeology as such, because in certain cases, it's okay to sample objects, but if it's something that's considered heritage, if it's something that's entered a museum, then it might be very difficult to get a permission to sample an object or do anything that's destructive, even if it's the tiniest of the tiniest of inferences. Because also, unfortunately, many people in museums, if they are just looking at artifacts, they might just not be aware of what techniques are out there or how much the techniques are just developing. And so it's important to communicate archaeological science to curators as well, because then there's better understanding of what's possible, and actually some of the techniques might not be as invasive as they think. But neutrons are completely non-invasive, and they can penetrate through several centimeters of the sample, so you can get an information about a bulk composition, for example, of that sample. They distinguish different isotopes. You can look at the structure inside in case of neutron tomography, and also things like strain and stress, which is important for me because my research is about ancient technology. So I'm looking at how the swords were made, how they were cast, cases where swords were made of different metals together. And you can also look at things like conservation status, because neutrons see light elements, which means that, for example, you can see layers of corrosion and kind of assess that. And where I'm doing my research is on IMAT and INES, which are two instruments at ICES Neutron and Muon source in Oxfordshire. And IMAT is an imaging instrument where I'm doing neutron imaging, while INES is a neutron diffractometer. But there are other neutron sources as well. Here's us mounting one of the swords for imaging. And the choice of the source will really depend on different factors. Like, for example, in my case, the swords were trafficked here, and because of their kind of gray status, if we wanted to analyze them, for example, in France, it would be impossible because they can't cross the borders. They don't even belong here, right? But if they're already here, we can use ISIS. So in a way, it's lucky that they were trafficked to a country with a neutron source, although I wish they were never trafficked at all. And then the question is, what kind of instrument is needed for your purposes? And again, whether the objects can travel at all. Because in case of bigger objects, the museum might require you to travel with them and be present for the entire experiment. Or they might want museum personnel to travel with the object and be there all the time and keep it really secure. Or if it's smaller samples or just small objects, they can be sent to an institution and be analyzed by the instrument scientist, and there might be no need for anybody to travel with them. So it kind of depends on things like funding as well, and what arrangements the institution, the Neutron Institution has with perhaps the country where the scientists are from. So there's different factors to think about here. And the most important thing as ever, I always say that, is to talk to the instrument scientist, because they will help you understand what the instrument can do, what are the limitations, if the instrument is applicable to what you want to see. And you might even learn what answers you can actually get from the instrument that you might have not realized before. So just talk to the instrument scientist, and hopefully not 2 days before the proposal deadline. And here are some of the facilities that use neutrons for cultural heritage. One of them, the one in Germany, is not quite operational right now, and one is under construction currently. But ISIS, ILL, PSI, they're institutions that have instruments that can be used for cultural heritage, and sometimes more instruments can be used, but it's also the case of whether people working there have any experience with cultural heritage. Because otherwise, if you yourself are not very familiar with the technique, it's much more difficult to then know what you can actually achieve. Now, something to mention here is mounting of the objects, because it's one thing to write a proposal, and proposals are generally twice a year in different institutions. And if you apply for them, you will be considered by a panel. And then if you get beam time, then you're in luck and you kind of can do the analysis. But before that happens, there's so much more to be done, even before you even talk to the instrument scientist. But if you get beam time, one of the things to talk about and consider is how you're going to mount the object. Because, for example, in the case of my objects, it was very easy because ISIS have kind of a long history of analyzing, weapons, swords and specifically. So there are already frames that were made. Someone has already done the work of thinking about how you're actually going to mount this object. So on the left, you can see me with one of the bimetallic swords, and it's just a simple aluminium frame because aluminium is transparent to neutrons. And then you can clamp the object, and there's foam there, so it doesn't actually, hurt the object. And it's pretty straightforward. Sometimes you can just place the object flat, depending on its geometry and what the object is. Or on the right, we have an example of how we mounted an object for neutron tomography, which is again in an aluminium tube because it's transparent. And we kind of wrapped it in aluminium foil to make sure it doesn't slide, and it's just kind of firmly, because it's an imaging technique and the object is rotating, so it shouldn't move. But in case of smaller objects, what I've seen is them just being wrapped in little aluminium pouches, and then they are set on that frame. And you can automate the measurement just by moving the table, because they generally move in all directions. So sometimes it's really quite straightforward. If it's something flat, for example, the more complicated the object, the more complicated it is to measure. But thankfully, there's a lot that can be done by rotating it and just kind of observing it. And speaking of observing, I wanted to talk to you about one case study that I did with so-called split ear pommel swords, which are this type of sword you can see here in the picture with those eared pommel. That's why it's called that. And they can be either fully bronze, like the one on the bottom, or bimetallic, so with a bronze hilt and an iron blade. And you can see on the top picture that iron blade is quite heavily corroded, when the picture in the middle is gone completely. It's corroded away. And they are generally found in northern Iran, but also in Armenia and Georgia. And we had swords of this type. And here are just a few examples. And we knew we eventually wanted to analyze them with neutrons. But it's better to first understand the objects a little bit better so the neutron analysis is done to its full potential. So the first thing we did, like looked really carefully at them, because you can just get so much from just observing the object, trying to understand it, to really know how to then proceed. So in the case of this object, we knew the blades didn't quite match the type of the sword. The sword in the middle has a blade at a 90-degree angle to what it should be. The sword at the top also, you could tell that there was iron inside the hilt. So these were some worrying signs. But before we did neutrons, we used an X-ray radiography machine, which was quite weak, but it was strong enough to be able to see certain things, which were, especially in the sword in the bottom, you see that the blade completely, how it's attached does not make sense for it to be usable. But I didn't quite understand what I was seeing from this picture. But I definitely had this, if my only question was the sword modified, perhaps this would be enough. But of course, I'm looking at ancient technology. I want to understand way more than, the condition of the sword or whether it's fully authentic. And then the sword on the top, you see that the guard, because it's almost white, it's transparent, it's empty, as opposed to the rest of the hilt, which is solid. And another thing you can see there is this liquid shape. And because it's stopped all the X-rays, and because of that liquid shape, it suggested to me that it might be lead. So this again told me something. I knew to expect lead, for example. And I knew that I really wanted a good tomography to fully understand what was going on. But we were lucky because they were not museum objects. So in a way, they didn't have any conservation treatment apart from that. But that is something to look out for. If you have a museum object, especially an object that's been in the museum for a very long time, some consolidants might have been used to keep it together, which will really affect neutron measurement, especially neutron diffraction, because they're often high in hydrogen. So it might just highlight, all you might see will be that consolidant. It's not completely dire. If it's not permeating the entire object, if it's just on the surface, it can be removed slightly. It might not be too bad. But if an object is fully permeated with a consolidant, it might be impossible to do the measurement. So it's definitely something to look out for, because it's one of the things that can really delay you or, render the analysis completely impossible. So this is what you saw from the X-rays. And this is what we could see with neutrons. So what you're seeing here, that indeed the hilt has an iron core inside, which is actually remnants of an original iron blade. You can also see indeed that that part of the guard is hollow, so I believe it's been fully added later. You don't see the lead here because the lead is weakly attenuating, so it's really dark gray, but I'll show you in a second. And you can also see that that blade was indeed added at a 90-degree angle to the original blade. You can see bubbles in the cast, which can tell you something about how the cast was, how the mold was arranged when the sword was cast. And nicely, you can see as well where that a little bit of iron was exposed in the pommel, because the pommel has holes that go all the way through. You can see how much more corroded that part of iron is in relation to the iron that's been embedded in the bronze. So these are all things that you can kind of learn apart from the fact that they're modified. You can really see some information about how that sword was cast. What you can also see, perhaps, is the little striations in that iron, something to tell you about how it was forged from kind of like lengthwise. And to show you the lead, I marked it in green, and this is what holds that blade to the new hilt. This is the example on the bottom. And here you can see as well that it's a bimetallic sword where the original blade was iron and you have remnants of that blade inside. You can see the newly added bronze blade. By the way, I believe that all those blades are also ancient. There was nothing to suggest that they weren't. So there were some blades that were lying around probably when other swords were discovered. There might have been some blades deposited, or they might have just been blades which originally had wooden hilts, and those hilts could have withered away. But either way, the blade was replaced, and the sword now looks like a bronze blade, like a bronze sword, but it was actually bimetallic. So it's not only is just damaging the object, it's also obscuring its true nature, which then, in the long run, obscures our understanding of bimetallic technology in Iran and how well people actually connected those two metals and how common it was, because it really must be more common than we thought originally. But what you can see as well is this, which we could see just a faint shadow of some sort on the X-ray radiography, but it's a drill bit with those grooves, a very standard 2.1 millimeter drill bit. And if you slice the object sideways, you can really see that rotation of the drill. So it probably, there was an attempt to drill through the sword and the drill broke, perhaps, because I can't imagine someone tried to use it as a pin. And then the third example is the sword on top, also bimetallic. And here you can see the glue very well. You can see it has this liquidy appearance. And you can also see a thin layer of corrosion on the surface of the iron inside, as well as the corrosion that's much more intense, where there is a hole, probably a casting flaw in the iron. And the interesting thing you can see as well is where you have that iron tang, where there is that original casting hole, it's very corroded. But then you look closer to the blade, you have no corrosion, where there is a gap, because that gap is a modern gap. So there was no time for the corrosion to happen. And to show you what you can do with data like this, because it's one thing learning about the object you're researching, but another thing is being able to show it to people, show your results, and try for them to reach as many people as possible. So one of the things you can do with such data as well is cool animations like that, where you can really see that iron. You can play with different colors and everything. You can do really cool things, but this is just nice to show you in 3D how that glue works, and how that sword was cast as well. But it's not like X-rays are better than neutrons. They are complementary techniques. So for example, here, you can see this quite interesting iron sword, bronze sword, sorry. And you can compare, we did X-ray tomography and neutron tomography. And there is a clay core there, for example, in that cone shape. So you can really see what's going on. You can see the bits inside are iron. And on the neutron tomography slice, you can see that it's corroded on the surface, and one is more corroded than the other. I'm still trying to understand what happened there, how that sword was actually made. So if just by looking at this for a few seconds, you might have an idea of what's going on there, please do let me know. My email will be at the end of the presentation. But yeah, it's one of these things where you can really compare certain things. And we also had an example, for example, of a sword which was actually quite highly leaded bronze. And you could immediately see that on an X-ray. That lead content really affected how we were seeing what was inside the object, whereas neutrons had no issue with that lead in the bronze at all. So it's if you have the option, absolutely do both. And if you don't have an option, for example, to do neutron tomography, do X-ray tomography, and then do neutron diffraction if you can. Because if you're doing neutron diffraction, so if you're looking at the phase analysis, any imaging is useful. Even a radiography might be useful, you know. So the more you can learn about the object before you use neutrons, the better, because neutron time is very limited. So if you come in to the facility knowing as much as possible, it will be just so much easier in the long run for you to do the analysis and kind of understand what you're doing. And another case study, which I'll focus on neutron diffraction for, is a case of iron mask daggers, which are this very specific type of dagger or sword from Iran, because dagger, sword, it kind of just depends on the length of the object. So these are a bit broken, but still it's in between. They're called that because of a decoration on the face, on the pommel. It's two faces facing outwards. And unfortunately, they were widely looted from 1920s onwards. They're believed to come from Luristan, the province in Iran, famous for its bronzes as well. But unfortunately, there is only one example that's known from a specific site, and that site is Babijilan, which is indeed in Luristan, but it's a surface find. So you have not a single fully provenance excavated example, which is annoying to say the least. But that also means that the two sources that we have are just two of many that had the same fate. And you can see in that cross section, that's to show that these swords are actually made of many different elements. It's a similar type of sword, and you can really see it's not just forged together, it's composed of many different elements. And this is how they've been analyzed in the past. They could just be cut in half, or a large chunk could be cut out of them. And that's still done for metallography very often, for much more corroded objects, much less important objects in a way than the complete sword might be. But we still want to avoid that, especially that these swords are made of many different elements. So if you try to get an accurate reading of its composition, perhaps, or carbon content, you would have to sample every single piece. And they're known to be composed of up to 14 pieces, for example. So it's kind of impossible. So here you can see, indeed, different swords or samples. Sadly, swords were bought as well for the purpose of analysis. So for example, actually the sword you can see in the picture, that sword was bought to be analyzed by now. In the 60s, it was different types. Hopefully no one does that at this point. And if they did, hopefully no one would publish it. But we had the option of doing it completely non-destructively. So here's an example of the spectrum that we got. And that's also a good opportunity to mention data processing of such data, or processing of such data, because what you get, you generally have different banks which will measure the neutrons scattering from the object, and you'll get patterns which correspond to different despacings, which will then tell you the distance between them, from which you can gather what phase you're dealing with. So here we have different phases of iron, or mostly in this case ferrite and a little bit of magnetite and goethite. And that's an example of a well-preserved sword, all in all, even though on the surface it didn't look quite well preserved. And the refinement you're doing will fit the model to the data that you have. And there are certain mathematical operations you can do to kind of really try to fit it as well as possible. But there's, of course, limitations. And one of the limitations is just how much time it takes. You can't just look up the parameters necessarily and think, okay, that's the phase. You kind of have to look around for what phases are present. And depending on whether the object is corroded or whether you struggled to align it properly in the instrument, it might be quite time consuming. But in the end, it's worth it because I didn't make 16 cats into my sword, for example. And this is an example of a neutron diffraction of a bimetallic sword. So one of the swords that you saw earlier, it had iron inside. And to me, it's completely inconceivable that you could analyze that iron without any sampling, but you can with neutrons. So what you're seeing here, you're still seeing those peaks for ferrite. So those very thin, long, narrow peaks. But because that's what we focused on. But you're also seeing those wider peaks, which are the bronze that surrounds it. So you can gather that information even though that iron is inside bronze, which does kind of move around the data, but it's not really a massive problem. And you can get information about the bronze as well, with their dendritic structure present. And you can calculate carbon content from that phase analysis. Because, for example, here, what we did with the swords, one of the questions was whether there's any evidence of intentional carburization. And to do that, again, that's a kind of case where you'd have to measure different points along the blade and compare them with points on the hilt to see if the points along the blade have higher carbon content. Because if you try to do it intentionally, that's where you'd want the sword to be reinforced. But you can see here, from the information we've gathered, that the highest levels are actually in the hilt, and the blades aren't higher in carbon at all. But of course, you have to keep in mind it's not a perfectly accurate measurement because of the corrosion and because of the difference between corrosion of ferrite and cementite, which are the two phases that you use to calculate the actual carbon content. But if there is an error, it's consistent. So that would still wouldn't change the fact that there is no evidence for intentional carburization of these swords. Yeah, as I mentioned, though, you have to really be prepared for things like the neutron beam not being available. The last time I did analysis, everything worked perfectly, and it shouldn't be so surprising, but it was because it's such a complicated facility. There's so many things that could be going wrong, and if even one of them goes wrong, you're just losing beam and using beam time, which hopefully you can get back. But if it's the case of funding, if it's a case of objects having to move borders and stuff like that, it might be tricky to reschedule. Thankfully for me, it wasn't, because I'm here, the objects are here, we can wait up to a certain point. But yeah, you have to be prepared that you might not have the beam. Or if everything is correct with the beam, you might have issues with the instrument itself. Shutters, if you have camera, there might be issues with the camera or the lens. In case of neutron imaging, you might have issues with sourcing the objects, especially if you're liaising with a museum. There might be issues there, or I don't know, on the border, again, with bringing the objects. Or you might think that you've aligned the object properly, but you haven't, and it might be necessary to repeat the measurement. Or you might find something that you haven't expected there, and that can delay your measurement. Because, for example, you might find high levels of an element which will make the source more irradiated, because neutrons do irradiate the object, but in case of bronze or iron, after a few hours, even less, the object is safe to touch and safe to be moved and perhaps sent back to the museum. But if you have something like very high levels of arsenic, and you suddenly irradiate the object, then that can extend to many days. So PXRF, for example, would be something very good to do as well. If you suspect at all that the object might have higher levels of arsenic or some other elements, which would attenuate the neutrons more. And as I mentioned, yeah, the processing data is a tricky thing, both with diffraction data, but also imaging data. There's just so much information that can potentially learn from imaging data that it really will take time to process it to its full potential. And of course, you may just make mistakes of your own. So really think of having a backup. So for example, having extra objects. If, for example, you discover that what you wanted to analyze is more corroded than you expected or more fragile than you expected, or if suddenly something have higher level of arsenic and things like that. And to finish off, yeah, I wanted to show you what is a human error in the sense that it's something that should have never happened, where a sword was drilled into just so deeply, and then a new blade was inserted. And what you're seeing, that highly attenuating white material, is just loads of glue. So much so, in fact, that you could see it on the surface. There was a darkening of the blade because of that glue. So it might be our own error, but there's also errors that might have been done in the past. And that's all from me. If you have any questions, please do let me know. I just wanted to thank my supervisors, previously mentioned Anna Federica and Antonella Scarillo, and also Nat Satullo and Andrew Shortland from my university, and Dr. St. John Simpson from the British Museum, who have helped me make this research what it is.